So let us discuss meter bridge. So look at the diagram here. So it contains 1 meter wire that is fixed between 2 points, say A and B. This point is A and that point is B. This is 1 meter wire, and there are 3 metallic strips here. So one metallic strip here, this is one, this is one metallic strip, and in between there is one more metallic strip here, and there are 5 connecting points. So let us say this is one connecting point, this is 1, 3, 4, 5 connecting points. See, there are 2 gaps here. This is one gap and that is one gap. You can connect a resistor or any wire here across these 2 points, and you can also connect one more resistor or one more wire across these 2 points. So a meter scale is also attached at the bottom of the wire. So this is the meter scale. This is the meter scale. Meter scale. So this is the meter bridge, and from here we will connect jockey through the galvanometer. So from here let us connect a galvanometer. Through galvanometer let us connect a jockey. Jockey is like a metallic rod with a knife edge, so that can you can move that jockey on this wire. You can slide this jockey on this wire. So this is what your circuit can. So this is what your meter bridge structure. So everything will be fixed on a wooden platform. So let us take wooden platform like this. Everything is fixed on a wooden platform. It's a wooden platform. Now let us connect a battery from here. Connect a battery. So maybe rheostat. From here, even you can connect in between a switch. Even switch, and then let us connect. So once you connect a battery here, then current will go through this wire. Current will go through this wire, because once you close the switch, then current will go through this wire, because this is a closed circuit. So you can adjust current in this wire by adjusting this rheostat here. By adjusting rheostat, you can alter current going through this wire. Now this is the meter bridge, and this is used to measure, or this is used to calculate or estimate resistance of unknown resistor if we have one known resistor. So let us take two resistors. And resistance of known resistor is, let us say, S. S is resistance of known resistor that I am connecting across this part. And one more resistor, unknown resistor, I am connecting, let us say, here. This is unknown resistor. Say R is the resistance that we need to estimate. So look at this. Now when you close the switch, then current will go through this wire, and if this jockey is not touching here, and a part of current will go through this, and a part of current will go through this one also. So there are two lines. From here current will go through this line, and similarly current can also go through this line. So if I is total current provided by this battery, a part of I will go through this, a part of I will go through this. If this jockey is not touching here. If the jockey is touching here, and if jockey is touching at some point, then this is like a Wheatstone bridge. And see how it is behaves like a Wheatstone bridge. Now this is the battery. Now there is a connection here. So up to here, this behaves like a small resistor, and that behaves like a small resistor once again, and there is one more resistor here, and there is one more resistor, and from this, and there is one more connection to this point through galvanometer. So this looks like a Wheatstone bridge. As you alter this point as you slide this jockey on this wire. At some point, as you move this point on this wire, for example, if it is touching here and this part behaves like a resistor of resistance R, maybe X prime, and that part behaves like one more resistor of resistance X double prime. As you change this point, maybe if you slide this jockey on this wire, then length of this part and length of that part changes. When length of this part and that part changes, then resistance of this part and that part also changes. At some point, as you keep on searching, as you keep on moving this point on this, at some point you will find no current through the galvanometer. So it means that the bridge is balanced. Whenever bridge is balanced, it means R by this resistance equals to S by that resistance. Let us take resistance of this part is X prime and resistance of that part is X double prime. Then you can write R by X prime equals to S by X double prime. So let us write here R by X prime equals to S by X double prime. Now our aim is to find R. Then R becomes X prime by X double prime into S. And in this, R is unknown resistor, that is what we want to get, and S is known resistor here, and X prime is resistance of the wire here, this wire, left side, and X double prime is resistance of the wire right side to this jockey, right side to this part. And assume that if I found no current at length L from A, let us say if that length is L, now I am finding at a distance L, when I keep my jockey at a distance L from A, I found no current through the galvanometer. Then resistance of this part X prime, that X prime will be now is rho L by A. So rho is a specific resistance of this wire and A is area of this wire and L is length from here to there. Similarly, you can write down X double prime equals to rho. Then if this is L and whole length is 1 meter, if L is measured in terms of centimeter, now you can write down the remaining length as 100 minus L by A. Here A and here is also A because the area of wire is same throughout the wire. And resistivity is also same because the wire is made of same material. So then X prime by X double prime equals to L by 100 minus L. So this implies R equals to L by 100 minus L into S. This is the resistance of unknown resistor. This is how we can find the resistance of unknown resistor. So let us look at this question. Look at this question. In a meter bridge experiment, null point is identified at 36.7 centimeter. In this, first null point is observed at a distance 36.7 centimeter from here. Now 12 ohm resistor is connected parallel to S. Now we are connecting 12 ohm resistor parallel to this S and again searched for null point, and it is at 51.9 centimeter right now. Find R and S values. So initially we don't know what is R and what is S, but we have connected R here and S here. Then we searched for a balancing point. We got a balancing point at a distance of 36.7 from here. When we connect one more resistor, 12 ohm resistor, parallel to S, we found balancing point at 51.9 centimeter. Now we need to find what is R and what is S. So first let us say, first balancing point is identified at 36.7 centimeter. And if this is 36.7 centimeter and remaining length becomes 66.3. So you can write down that is R by S, that is R by S equals to 36.7 by, then 100 minus 36.7 is 66.3. So this is what your R by S value. Now next time what we are doing, next time we are connecting one more resistor here, 12 ohm resistor parallel to S. So once we connect 12 ohm resistor here, then resistance of this part will be equals to, because 12 ohm and S both are in parallel, so you get a net resistance of that resistor will be equals to 1 by 12 plus 1 by S. So now X will be equals to, now X equals to 12S by 12 plus S. This will be our next new resistance. So now, so when resistance of the resistor at second gap is this much, then we found the balancing point is at 51.9 centimeter. So let us write, there is no change in resistance of resistor which is connected at left gap. Then you get R by, then instead of S we got now this X is 12S by 12 plus S. So you can write down 12S into 12 plus S, that equals to, then balancing point is obtained at 51.9 centimeter by, then 100 minus 51.9 is 48.1. So this implies R by S into 12 plus S by 12 equals to 51.9 by 48.1, 51.9 by 48.1. So now we know what is R by S value. So once you fix R by S value from here, that is 36.7 by 66.3 into 12 plus S by 12 equals to 51.9 by 48.1. So once you calculate this, your S will be, the value of S will be, see, because everything is given except this S value, so you can compute S value. Once you simplify this, SB will be 13.5 ohm. So once you know S, from this equation you can also compute R value. So that implies R value will be 6.86 ohm. This is the answer. Now look at potentiometer, and this is the instrument by which you can find out voltage across any element in the circuit. So look at the structure of this potentiometer. Look at the structure of the potentiometer. It contains many wires of length 1 meter. So let us say here, this is a wire of length 1 meter, and let us arrange one more wire like this of 1 meter length, and one more wire and one more wire. Here I am taking only four 1 meter wires, but in general potentiometer may have even 10 1 meter wires. So let us consider this point is A, and this point is, let us say, B. So let us connect all these wires. So I will use metallic strips to connect all these wires. Let us take one metallic strip and connect here. So if I connect metallic strip here, and this whole thing becomes like a single wire, this will be like a connecting wire, and see, this is 1 meter and that is 1 meter, then you get 2 meter wire. Now if I connect one more metallic strip here, if I connect these 2 points by one more metallic strip, then your length becomes 1 meter, 2 meter and 3 meter. Now I will take one more metallic strip and I will connect here, then your total length becomes 1, 2, 3 and 4, like that. But in general you may have even 10 such wires, then your length of the potentiometer may be length of potentiometer wire may be even 10 meters. Now for simplicity I am taking only 4 meter wire. Now let us, even you can attach a scale here. You can attach a scale here for to know the length. Now connect a battery. Let us connect a battery from here. Let us connect a battery, and you can take here rheostat. You may take even a switch, that's rheostat. So now, when you close the switch, then current goes through the circuit, because this is a closed circuit now. This is how current goes. When you close the switch, then current goes through the circuit like this. So you can alter the current by changing this rheostat. By adjusting this rheostat, you can alter current that is going through this wire. So assume that for particular adjustment, say V is voltage across A and B. If V is voltage across A and B, V is voltage across A and B. And length of the, in general, length of the potentiometer, you can take it as L. Here you can define potential gradient. Potential gradient, that is potential change in potential per unit length. So that is V by L, because L is total length of the potentiometer wire, and V is voltage across that wire. So potential gradient will be V by L. So phi is potential gradient, that is V by L. So if it means that if you move your point from A by distance 1 meter, you will find this much potential gradient. If you move your point from here by 2 meter, then you will find 2 times this phi. So potential gradient is defined as change in potential per unit length. So unit for that is volt per meter. That's the unit. So now the total voltage drop from A to B, in between A and B, is V, and length is L. So this is voltage drop per unit length. So potential gradient. Now this instrument is used to compare EMF of 2 batteries or 2 cells. Let us see how we can do that. Let us take a connection from here. Now first I will try to compare EMF of 2 cells. Compare EMF of 2 cells or 2 batteries. Let us do that. Let us take connection from here. Take 2 connections from here and connect one battery here and connect one more battery here. Say E1 is EMF of first battery and E2 is EMF of second battery. And from here let us take, this is a two-way key. Then from here you can connect a galvanometer. From galvanometer you can take a jockey. This is the jockey. Now you can move this jockey on this wire. See, let us look at this circuit. So now if this jockey is not touching the wire, then you have only one circuit, that is this part. If the jockey is not touching this wire, then you will be having only one loop. This is the loop. Right? Now this is a two-way key. If you keep it in on mode, then E1 will be ineffective. If you keep it in off mode, then it will, then E2 will be in effective mode. If you keep on, this will be effective. If you keep off, this will be effective. At the same time, two batteries cannot work. If you keep it on, E1 will be effective. If you keep it off, E2 will be effective. So that is the two-way key. So now, so let us keep first E1 in active mode. Once you keep E1 in active mode, then you get one circuit, primary circuit here, and now secondary circuit is going like this from here to here. Then galvanometer. As you move this jockey on this wire, at some point you will find no current through the galvanometer. Assume that this is the point. At this point you found no current through the galvanometer. So it means that the voltage across this point and that point will be equals to voltage across this point and that point. Assume that the connecting wires are having negligible resistance. Even you can apply Kirchhoff loop rule here. Let us take, then if you got balancing point at this point, balancing null point or null point at this point, so there is a loop here. You can see the loop here. The loop is from here you can start and you can go like this and you can go like that. There's a loop. If you start from here through battery and through this switch and through galvanometer and to the wire and from here to there, this is the loop. So say that point is, let us say C. Then let us apply a loop rule here. I am taking loop, this loop. See, this is the loop. Then voltage across, see, this is connecting wire and this is connecting wire, and connecting wires are having negligible resistance. Then only elements you have in this circuit is one battery and one wire. Then voltage across this one is E1. That's E1, and from here to there, because the voltage here is higher than here, as you go from here to there, voltage drops. When voltage drops, then this voltage must be less than that voltage, so you get negative. That negative times then this voltage drop. Then what will be that voltage drop? As I said, this is the voltage drop per unit length. Now assume that this length is L1. If that length is L1, then your voltage drop will be 5 into L1, that equals to 0. This is what our first equation. Now let us take second equation, second mode. Now you keep this one, you keep E2 in effective mode. Now the circuit is, E2 is now in effective mode. Now this is primary circuit once again. Now this is the second circuit. Now as you move this jockey on this surface, now let us see, for next case, assume that you are finding a balancing point somewhere here, let us say. So this is the next time jockey, second time. This time, this is the jockey you are finding. So now you take loop here. See, from here I am starting, from A through battery, through galvanometer and up to here, and from here this path. This is the path. See, from here through the battery and through the galvanometer and from here and through this way. This is that. So you can apply once again. So for this position, you found no current through the galvanometer. So assume that this length is L2 from here. That you can read from the scale L2. Then you can write down. Then all connecting wires has got negligible resistance. Then only elements you have in this loop is battery and this wire. So across this battery, potential drop is E2, and there is no drop up to here. And from here to there, because this potential is less than that potential, then we know potential gradient is phi and length is L2 here, length of the wire. Then you get total potential drop will be phi L2 equals to 0. If you solve these two questions, you will get E1 by E2 equals to L1 by L2. This is the equation. So by this you can compare EMF of two batteries. If you know EMF of one battery, you can find EMF of second battery. So this is one application of potentiometer, compare EMF of two batteries. Now you can also measure internal resistance of the battery by potentiometer. Let us see how we can measure internal resistance of the battery. So measure internal resistance. Internal resistance of battery. So for that, let us take once again a potentiometer. As I said, potentiometer contains many wires of 1 meter length. This is that. So these are metallic strips, one metallic strip, and this is one metallic strip, and there is one metallic strip. So this is point A, and let us connect, and this is point B. Let us connect to the battery here, and there is a rheostat. So let us say this is point B and there is point A. This is the potentiometer structure. Now to find internal resistance of the battery, let us take the battery and connect from here. Let us take a battery and connect from here. And you can also connect one known resistor here. Let us say resistance of that resistor is R, and let us take here key. So from here combinedly you can take the galvanometer and the jockey. And the jockey can be slided. So you can slide this jockey on this way. Now first let us open the switch. When you open the switch, then this circuit, this line will be inactive. When you open the key, this line will be inactive, and say E is EMF of the battery. You can search for the balancing point. Once you search for the balancing point, as I said from the previous, the potential gradient is phi. The potential gradient is phi. When you search for the balancing point, assume that you have got balancing point at this point. At this point, let's say that length is L1. Then this is like a closed circuit. Now you are getting balancing point at this point. Say this is L1, and now this behaves like a closed circuit. It means the potential drop across this one must be equals to potential drop across that one. So that is E minus phi L1 equals to 0. Maybe L. Okay, let us say phi L1 equals to 0. Phi L1. So at distance L1, I got a balancing point. So now when you apply loop rule, you get this result. Next time what I will do, I will close the switch. When I close the switch, current will go through this resistor also. Then whenever current is going through the resistor, then the voltage drop across the battery will not be E, it will be something less than that V. See, already we have explained, whenever you take a battery and when you connect a resistor to the battery, so if R is internal resistance of the battery and E is EMF, then voltage, whenever, if the circuit is open, then voltage across the battery will be your E, because there is no current. Whenever you connect a resistor, then voltage across this battery now becomes E minus IR. E minus IR. So now some current is going through this resistor, then voltage across the battery now becomes V. Now you will find balancing point, let us say at a distance L2 now. Then voltage across the battery is V. You can apply once again Kirchhoff loop rule. Then voltage across the battery is V, and there is no voltage drop. And from here to here, then voltage drop will be minus phi L2 equals 0. So from these two, from here you can write down that E equals to V plus IR. From here you can write E equals to V plus IR. So let us substitute that here. V plus IR, V plus IR equals to phi L1, and for this one V equals to phi L2. So you divide these two, you get 1 plus IR by V, that equals to L1 by L2. So V is voltage drop across battery. The same voltage drop across, you see the same voltage drop across the resistor also. Then I is current going through this resistor. Then Ri will be equals to, if you apply Kirchhoff loop rule here, then V is voltage drop across this battery. Then the same voltage drop you will see across the resistor also. I is current going through that resistor. Then you say V equals to IR. So if V equals to IR, then you can write 1 plus IR by IR equals to L1 by L2. So that implies R by R equals to L1 by L2 minus 1. L1 by L2 minus 1. Then now your R becomes R times L1 by L2 minus 1. R becomes L1 by L2 minus 1. So this is the internal resistance, and we know what is R. R is what you are connecting here, and L1 is balancing point for the first time when you open the key. L2 is balancing point when you close the key. So look at this problem. A resistor of R ohm draws current from a potentiometer, and potentiometer has resistance R0. A voltage V is applied to the potentiometer. Determine an expression for the voltage across R when sliding contact is in the middle of the contact point. Look at the diagram here. So the potentiometer wire has resistance R0. Say this is the wire, and the resistance of this wire is R0, and the voltage drop across the resistor is let's say V. V is voltage drop, maybe here V and here 0, then voltage drop will be 0 V, or I can say simply like this, V is voltage drop. Now here this is the potentiometer. So potentiometer, resistance of the potentiometer wire is R0, and V is voltage across the potentiometer wire. Then a resistor of R draws current from this potentiometer. So like this. So this is the resistor of R is drawing current from here. Now we need to find voltage across this resistor when the sliding contact is in the middle of middle of this wire, say. So determine an expression for voltage across R when sliding contact is in the middle of this wire. So when sliding wire, see, you can slide this wire on this potentiometer wire. When the sliding wire is exactly at the center, what is the voltage drop across this resistor? This is the question. So to answer this, you need to find potential across this point and that point. So whatever potential you see across this one, you see the same potential across that one. Now assume that your voltage difference is supplying current I. If I is current that is coming from here, then there are two connections, one from here and one from here. A part of current will go here, say I1 will go there, then I2 will go through this resistor, and combinedly you get I here. Because I1 is coming here and I2 is coming here, so both will combine here, then I will go there. Then I equals to here I1 plus I2. Now let us estimate what is I. First let us estimate what is I. So to find out what is I, first you need to find out equivalent resistance of these resistors. So now this point is exactly at the midpoint. So total resistance of this wire is R0. So this is at exactly at midpoint. So it means left side of this point will have resistance R0 by 2 and right side will be R0 by 2. And now this R0 by 2 and this R both are in parallel. And let us estimate what is that resistance of this net resistance of these two, because this R0 by 2 and R both are in parallel. So then net resistance of that is, let us take 1 by R prime equals to 1 by R plus, this is R0 by 2, or you can write 2 by R0, that equals to R0 plus 2R by R0. So now resistance of this combination is R0 by R0 plus 2R. So now this is the equivalent resistance of these two resistors, and this is in series with that. Then net effective resistance will be now R double prime. R double prime will be equals to, this resistance is R prime plus that resistance is R0 by 2 once again. Then R double prime equals to, R prime is this, R0 by R0 plus 2R plus R0 by 2. So once you find this part, you can take a 2 into R0 plus 2R, then 2R R0 plus then R0 square plus 2R R0. So R double prime will be, you can write down R0, you can write down R0 square plus 2R R0 and 2R R0, that is 4R R0 by 2 into R0 plus 2R. So that equals to, you take R0 common, then R0 by 2 can be common. Then now it is R0 plus 4R by R0 plus 2R. This is effective resistance of this combination. Now you can estimate what is current. Now V is voltage across, this is resistance of the whole circuit. If this is the net resistance of the whole circuit, now we know V is voltage across that circuit. So V is voltage across that circuit. So you can write down V equals to I into R double prime. Then R double prime is this part. R0 by 2, R0 plus 4R by R0 plus 2R. So that implies I equals to 2 by R0, R0 plus 2R by R0 plus 4R into V. This is what your current is. That is what current, net current going through the circuit. Now, so this is current going through this wire. If this is the current going through this wire, you can estimate what is voltage across, let us say this point is A and that point is D and that point is B. So then voltage across A and B we know. Then our aim is to find voltage across A and D. So you can write down voltage across AB equals to, here voltage across AB equals to voltage across AD plus voltage across dB. Then our aim is to find voltage across AD. So VAD becomes now VAB minus VDB. Then VAB is V. VAB is, let us write here, VAB is V, then VDB equals to, then we know the current I, we know the current I, and we know this resistance, that is R0 by 2. So R0 by 2 times that current, R0 by 2 times that current will be your voltage across this point. So let's say I. So now VAD equals to now VAD equals to VAB, that is V, minus VDB. VDB is, we know resistance of this part, that is R0 by 2 times the current going through this line. The current is this part. So it is 2 by R0, R0 plus 2R by R0 plus 4R into V. You can cancel 2 by 2 and R0 by R0. Then finally you can even take V common. Once you take V common, then you get 1 minus R0 plus 2R by R0 plus 4R. So that equals to R0 plus 4R minus R0 minus 2R by R0 plus 4R into V is there. Take V. So now then VAD will be VAD equals to, now you can cancel R0, 4R minus 2R is 2R by R0 plus 4R into V. So this is what your answer is. So this is the answer.